In this video, we will explore how to predict pricings using machine learning. With machine learning, there are two key challenges. Challenge number one is you need a clean, quality, reliable data set. Challenge number two is you need to know the best mathematical algorithm that fits that data. Now, to overcome these challenges, we will look to NumerAI as our case study. And NumerAI is a data science competition that provides its users with ready-to-use data and a recommended algorithm. Now, the video will be broken into three parts. Part one, we will look into the theory behind the recommended algorithm. Part number two, we'll look into a practical application of this recommended algorithm using NumerAI's datasets. Part number three, I will showcase a user interface I developed that helps users with no coding experience to generate and upload their predictions onto NumerAI. So let's begin with part number one, the theory. So in part one, we'll first review the gradient boosting algorithm, which is the main algorithm, which can be configured in multiple ways for regression or classification applications. We will then look at the tree gradient boosting regression algorithm, which is the specific configuration that NumerAI recommends to be utilized.
For the algorithm, NumerAI recommends using the tree gradient boosting regression algorithm, which is derived from gradient boosting. Now, gradient boosting featured in Jerome Friedman's 1999 paper, and it's a flexible machine learning technique that applies to two types of supervised learning. Type 1 is regression and type 2 is classification. Our focus will be on type 1 regression, which is used for predicting continuous output variables based on input features. So, for instance, we can utilize it to estimate the intrinsic value or the price of a stock as our output variable, and we can utilize input features such as the free cash flow, revenue, long-term debt, and many others as our input. Now, our case will be for a tree regression, which is a variant of gradient boosting, and it will focus on predicting prices based on given input features. Page 5 of the reference paper summarizes the base gradient boosting algorithm, which can be configured for various problems. The algorithm starts by initializing the model with a prediction, and then iterating through a for loop where each iteration it refines the prediction and improves it with each pass. A critical element to note is the loss function capital L, which is a measure of how well the model's prediction matches the actual values. In regression, the least square loss is the most commonly used loss function, and it calculates the average square difference between your actual and predicted values, with the goal of minimizing it, which in turn enhances accuracy, whilst avoiding the pitfall of overfitting. Noting that popular regression Python libraries utilize this as the default loss function if an alternative is not selected by the user. Page 7 of the paper, section 4.3 regression trees, details a configuration for gradient boosting algorithm which is fit for our purpose. Similar to the base algorithm, it's split into two base steps. In step 1, initialization, we set the initial constant value prediction as the median of the target values. In step 2, which is again an iteration, we enter a for loop for which we will be building regression trees iteratively. At each iteration will involve calculating the pseudo-residuals, which is simply the difference between the actual values and the current predictions, which for the first iteration will be the target value minus the constant value from step 1. Then we will start constructing trees using these pseudo-residuals and input features, for which the final leaf of each tree will be known as a terminal node, which will include the pseudo-residuals for the samples falling within that branch or region. Next step will be, at each of these leaves, we will calculate the median residual, which is also known as our loss function. And then finally, we will be updating our predictions by adding the median residuals for each region, scaled by a learning rate to prevent overfitting to the previous prediction. We will repeat this process for M trees, which is defined by the user, and the final model will simply be predictions that are the sum of the contribution of all the trees.
In part one, we've explored the theory. However, now in part two, we need to look at the practical applications of the theory using NumerAI's data. So first, we'll need to explore NumerAI's data and understand what does NumerAI provide us and what does this data look like.
NumerAI will provide you with free datasets that are clean, regularized, and concealed. On the screen, you can see a sample of the data provided, which will be used to train our model. Column 1 refers to an ID, which consists of generic letters and numbers, and these are the concealed stock IDs, meaning we could be looking at a stock like Amazon or Apple or Google, but we wouldn't know which. The second column refers to the era, which is a point in time measured in weeks. It starts from era 1 for that particular stock ID, but we wouldn't know the exact date this measurement begins. The next column, labeled as features with a number assigned, represents the quantitative attributes of the stock. This could be a price over book, it could be free cash flow, it could be price over earning, but again, it's concealed. It's important to note that NumerAI will provide you over 2,000 features for a given stock ID at a particular era. Whilst you can choose all of them to train your model will be heavy and you would need to use a cloud computer, virtual network, or a virtual notebook, as regular computers won't be able to handle training this many features or rows of data. And additionally, part of training the model involves identifying the key features that sway the accuracy of your model, so selecting them all might not be wise. The final column is the target price, which represents a measure of the stock market return for a particular stock item. In simpler terms, it measures how well a stock performs compared to the other stocks within the same sector. It's measured over 20-day intervals, which is the equivalent of 4 eras, and the aim of this competition is to be able to predict the targets using the features. It's important to note that the values under the target and features are not currency or ratios. They're regularized data points that are ranging from 0 to 1. And this is done to ensure clean and comparable data, which ties back to the earlier point about the challenges of having clean quality data for machine learning. When I discuss machine learning with others, they often ask, why can't we just apply machine learning directly? I explain that clean data is essential. They might mention scraping data from websites or utilizing API commands to download this data, but I remind them that it must be cleaned, regularized, and sorted in order to facilitate an apples-to-apples comparison. We've now reviewed the overall data for training our model. However, within NumerAI, there are 5 core datasets. Your feature files, which contain all the features you can select from, your training data, which is combined with your feature files for model training, your validation data, which is updated weekly, which you can use to validate your trained models, your live data, which you can use to generate live predictions, and then finally your meta model, which provides you metrics tailored by NumerAI to measure how well your model performs, including how well it predicts the market and integrates into their meta model. Now, for the remaining steps, we looked at the data that's provided to us by NumerAI, ready to use. Your second step is you need to now construct your model. You need to predict the targets using the features, and users can choose their preferred algorithm. Then you will need to now generate your prediction function, which is the deliverable that we'll be uploading into NumerAI. That's simply put a function that's wrapped in a pickle format, and it will allow you to upload a single file that will auto-generate live predictions. Then the model will be scored based on target correlation and its integration within NumerAI's meta model. Some key considerations. First is staking. Whilst you can do this without staking, NumerAI does allow you to stake with their specific cryptocurrency. However, this should be based on your risk preference, as you can win or lose. Do your research first. In my case, I invested a small amount, less than $20, which I was okay with losing and gave me the motivation to work on it. Second is data monitoring. You need to track NumerAI's website for the latest revision number and when they are applicable. For example, version 5 is currently out, but it's not applicable until September 2024, with version 4.3 still being the accepted format. For feature set and computing, when you're using all the feature sets, you would need to run this on a virtual network or a cloud computer, as a regular computer won't be able to handle them. So you need to be selective if you're using a regular computer.
So now we've looked at what NumerAI provides us in datasets. So now we need to look at the practical application of the algorithm. So what will happen in this video is we will look at the inner workings of this algorithm so that we can understand what usually takes place when this is running in a machine learning Python library type of environment.
Step 1 in the algorithm is to initialize our model with the median of the target values. On screen, that's just simply put the average of all the target values, which is the final column. In the case of the values on the screen, that's just 0.45, and that will be our initial prediction for all the data points. In the second step, we'll need to calculate the pseudo-residual. The pseudo-residual is the difference between the actual target and the last predicted value. For our first iteration, your last predicted value is the median that we calculated in step 1. And this is done for every row of data, as we can see on the screen. In our next step, we will construct our tree, and the tree construction will use the ID, the era, and the features and user-defined parameters. The final leaf of the tree is also known as the terminal node, and it will contain initially our pseudo-residuals. There could be more than one pseudo-residual, as multiple rows of data can fit in the categories. In the next step, we will need to calculate our median residuals. So for every leaf or terminal node, we will calculate the average of the pseudo-residuals within. And then finally, we will add the previous predicted target with the product of the learning rate, which is a value between 0 and 1, and the median residual for every region. The reason why we have a learning rate is that helps us avoid overfitting. And then finally, we will keep repeating this process for the number of iterations trees that is defined by the user, each time learning from the previous model until the total number of trees is reached.
The final step is to showcase you the user interface that would allow you to generate your prediction files and upload them to NumerAI with no coding experience. In this part of the video, I will show you how to download this application, how to use it, and then finally how to upload to the website.
You can download the user interface from my GitHub page. It's a single .exe file compiled using the basic bindsolver library in Python. The interface is structured into 4 tabs. The first tab is for data. At the top left, you'll see a list of all available datasets that can be downloaded using NumerAI's API command. You can then select the files and the folder to download the data into, ensuring that the versions are consistent. For example, as of mid-August, version 4.3 is the latest accepted, and the file should be in a .parquet format with int8 encoding, which is integers using 8 bits, except for the feature file, which would need to be in a JSON format. Version 5 will soon be accepted in mid-September, which then needs to be utilized. Once downloaded, the datasets will appear in the list below and automatically be distributed to the correct lists on the right-hand side of the page. You will then select your feature list, and from your feature list, it will automatically display a list below for your feature list contents, which is how many features you want to train your model on. NumerAI categorizes them for you, and at the bottom, you can view the number of features contained within each file. Then the user will select his training file, his validation file, and finally his meta model file before he moves on to his training tab. The training tab is where you'll select your parameters and preferred library. I've included 2 different tree gradient boosting libraries, the LGBM regressor and the histogram gradient boosting regressor. The latter is a popular library in scikit, inspired by the LGBM, and it's better suited for handling larger datasets. However, both libraries are based on the same underlying theory. On this tab, you'll specify your parameters, which would include your learning rate, the maximum tree depth, the number of trees to be constructed, i.e. how many times do you want the loop to run, and the number of leaves or terminal nodes. That's where the median residuals are calculated from your pseudo residuals, and the final parameter is the proportion of features to be used at each node split. It should be worth noting the default loss function, since we're not specifying it, is the least squared. But there are also additional parameters that are available. However, these are the core. And you can also train multiple models by separating the input values with a comma. Once everything is set, you can click the train model button. After training, you can view your results in a graphical and in a tabulated form. You will be able to see your input features. You'll be able to see the performance metrics defined by NumerAI. Finally, there's a download button on every row. When you click on every row, you'll be able to see the specific graph for the data. And there's also a 4th tab for the tables, where you can see the tables behind the data. Once you've downloaded the model that you're satisfied with, you can visit NumerAI's website, where you can create your own account and upload the file you've downloaded. From there, NumerAI will automatically generate live predictions daily. You can monitor your model's performance. For reference, here's an example of my model. I initially staked 0.2 of the NumerAI cryptocurrency and recently added 0.7 to the same model. I believe this is an error on my end, and staking it all on a single model probably wasn't the best decision.
To bring this into a conclusion, it's important to emphasize 2 points, and they're the same 2 points that are challenges with machine learning. It's the importance of high quality data. Even the most advanced machine learning models will not be able to process bad data. As someone once told me, gold in, gold out, garbage in, garbage out. The second is, this is a math exercise. It's not an IT exercise. You need to understand the math behind the algorithm and not just the line of code that you're going to be applying from Python. This particular case, it's an algorithm that's recommended from 1999. There are more advanced machine learning models, but they wouldn't be applicable to this type of data. And then finally, if for some reason you're hearing this, I'd just like to say thank you.